much for spoiling the first theorem, because originally we have proven the theorem for higher Lie groupoids, which are simplicial manifolds with certain Kahn conditions, but actually Florian Dorsch very recently proved that everything works even without the Kahn conditions, because simplicial manifolds are always Kahn near the total degeneracy. But I'll talk about, yeah, I'll take the official title here. Okay, and so the whole thing is based on an idea by Severa from 2009, where there was a construction proposed how to turn a higher Lie groupoid or a simplicial manifold into a DG manifold, which is more or less an L infinity algebroid. And basically the main statement of our work is the procedure always works, the functor one defines is representable. And, but I'll try to somehow motivate it a little bit from the very start. So, introduction. And basically one could ask the following question. Why is the functor which takes a smooth manifold and gives us its tangent bundle, why is it well behaved? And the answer one can give to this question is that it is actually a Hom functor in disguise. So it's a Hom of something into M, and I'll tell what the something is in a minute. And for the whole thing to work properly, one actually has to go to the world of graded manifolds and instead of Tm, talk about T1M. Maybe I will define what a graded manifold is, even though I shouldn't. So a graded manifold, for me, is essentially a Z-graded, graded commutative algebra, which is isomorphic to the section space of the graded symmetric algebra of the dual of some graded vector bundle, where the graded vector bundle, it's Z-graded and degree-wise finite dimensional. And we take the opposite category of it. So I took a definition to annoy everyone. In particular, I'm just somehow in the definition encoding the bachelor theorem, so we don't have to talk about exactly what conditions I would need on the Z-grading. It's basically another way of speaking of Z-graded vector bundles with finite dimensional components. However, due to this dualizing and looking at it as an algebra, our morphisms are not strict, so we can map multiple elements to one element.
So I don't think degree-wise finite dimensional. That's, I mean, that won't fit. That's going to be still pretty infinite.
Yes, yes. We for now, maybe at some point I will cut them on one side, but for now I won't. And so I usually use like curly M type letters for the graded manifold, and C of this curly letter for the algebra, but for me they are one and the same thing, so I'm just looking at graded manifolds as a subcategory of the opposed category of the appropriate algebras. I will give a few examples. So if M is an ordinary smooth manifold, there are two things we can do. We could define a graded manifold just by saying we look at its smooth functions. So then I'll just use the original letter. So manifolds are special cases of graded manifolds because the algebra of smooth functions knows everything about the manifold. Or we take the de Rham complex as an algebra, and this is something I'll denote by T1M, which is the T1M we saw before. More generally, if I start with a graded vector bundle, I will write V in bracket 0 for just the graded manifold whose sections are the things that we defined. And I'll write Vk for the one where I first shift the degree of the graded vector space by a certain number. Finally, as a sub-example of this, I will use the letter D for R shifted by -1. And so we have one generator in an odd degree, so the algebra will be just one formal additional generator, which squares to 0 and has degree -1. Sorry? In the function algebra, the degree is negative. I knew that this question would come. I think it will come in every talk.
Now I guess the questions make sense, so sorry.
It's going to make sense soon. So this is actually the D we had here. And so now this equality is almost well defined. I will note that this is an equality of presheaves. So, and when I say presheaf, I just mean set-valued functors. And this Hom is the internal Hom. So I should tell you about both things, how I can see them as a set-valued functor from graded manifolds. So T1M applied to some graded manifold will just be the graded manifold homomorphisms from T to T1M, which is defined here, and Hom dm of some test object is the homomorphisms from D times T to M. So, and basically this statement means that there is a natural transformation between those functors. In particularly, one could say the internal Hom is representable and the graded manifold representing it is T1M. This is actually true more generally. We could start with any graded manifold and just define its shifted tangent bundle by this definition, and then we would have to check that there is an actual graded manifold conforming to this equality. So theorem, let V to M be a graded vector bundle, then Hom D V0 is representable by well, I'll write it like this. V shifted by 1, the fiber derivatives, and Tm put in degree 1 as a graded manifold. So using my notation to annoy everybody, I'll write it like this. Okay, actually this is a theorem we had to prove because we needed to see exactly what choices we make on the way. In particular, the thing that we have is that a Tm connection on V induces an isomorphism. So we have that Hom dv0 is isomorphic to this, but a priori the isomorphism is not fixed, and to fix it we need a Tm connection on V, and once we kind of go really into the category and we need to see when our morphism is strict and so on, we'll need to check whether connections can be made compatible. Okay, the whole story is compatible with the D in DG, so I could talk about differentials, but I won't. Basically the idea of Pavol was that one can use the same approach, this D, which is called fat point or double point or infinitesimal line or many other things, to differentiate groupoids, higher groupoids, simplicial manifolds. And thankfully, Ezra has done a lot of my work on defining notions. Thank you very much. So I'll probably skip the definition of a simplicial manifold, or should I still write it up? Okay. So then I can actually write down the theorem that we have proven. If we take this infinitesimal point and create its pair groupoid, and then take the nerve of the pair groupoid, we get a simplicial manifold, which I'll denote by D. And then we take a simplicial manifold. And now we can take the Homs from this graded simplicial manifold into this simplicial manifold, which is in particular a graded simplicial manifold. And this is a functor, and now the statement is this functor is actually isomorphic to something. So it is representable. And isomorphic to the tangent complex.
This functor on graded manifolds?
Yes. Is representable, so it's going from graded manifolds to set. Thank you. And I'll say what it is. So it is the sum of the kernels of the tangent to the horn projection, all shifted into the respective degree. And for notation reasons, I'll explain what I mean by horn projections. Current TP x0.
Small question, because you said representable, but you write it as a covariant functor, so there's going to be a mismatch.
Sorry.
Well, we wrote representable.
So what I mean?
Representable,
Sorry.
representable is the opposite.
Okay. Thank you. I'm not very good at the co-lingo, so just dualize wherever you need. I'll write it down. So hom of t times d to x is supposed to be naturally isomorphic to hom of from t to this thing, which I'll call thoroughly t of x, because there are not enough t's in the business yet. Okay, so I should say that by horn projections, I mean the natural maps from the levels of the simplicial manifold to their horns, which are the homs from the horn spaces, the zeroth one always, into x. And those things do not necessarily exist in general. They will exist near the zero section, but I don't want to get too much into Florian's work, so I'll just say Kahn here. So Kahn simplicial manifolds are synonymously the infinity groupoid, where we suppose certain conditions on the simplicial manifold that assure that those things exist as manifold and that those maps are surjective submersions.
Sorry, what's the sum over?
Sorry?
You've got a direct sum sign. What's that sum over?
Oh yeah, it's k greater than 0.
Oh. What are you restricted to?
To x0, to the total degeneracy.
Could you write that? Thank you.
Soon my indices are going to have indices that have indices, so thank you for augmenting the font size once in a while. Okay, and the basic proof idea is that we're going to take this functor and approximate it by smaller functors from below. This is an idea that was already in the article by Severa, and then we inductively show that on each step we stay co-representable, or we co-stay representable. So I'm just going to call this thing h, and I'm going to write h as a limit of certain hk's, and hk of t will be basically a part of a morphism in here. So it will be a collection of maps, fl from t times d l to xl for l lesser or equal to k minus 2, and fk, which is going to be defined not on the whole of dl plus 1 of dk, but on star times d to the power k. So k minus 1 xk. And so it will be a collection of maps up until level k, where on the kth level we're only partially defined.
Could I know this is extreme, could you possibly use a different letter for the test set T than for the tangent bundle?
Yes. Yes. Okay. Each time you improve my notation, I'll use the next letter of your name. Okay, so there are, I don't want to write down the simplicial identities, like the identities which FL and FK have to satisfy wherever they are defined, but basically it's exactly that. It's the fact that S something, F something is the appropriate F something, S something, and the same with D, wherever defined. And
DL is what?
so those are degeneracies and phase maps.
The D, capital D sub L. What is it?
Sorry. So for me, the nerve of the pair groupoid.
Oh, D is that thing.
Yes.
Oh, sorry.
So and dl is actually d to the power l, which is, I'm sorry for that, l plus 1 copies of d. Yeah, and degeneracy maps and phase maps of the simplicial manifold.
You mean tensor? Sorry, no, D is a spectrum.
Yes. Yeah, so the algebra of functions here is an exterior algebra in L plus 1 generators, all in degree minus 1. Sorry? Oh yeah, DF, FD. Okay, so I will not write those conditions as formulas, but I will write them into a diagram. Basically, if we take hk minus 1, it has its top component fk minus 1, which sits in, so I'll take it on an E. So E times point times dk minus 1 to xk minus 1. And hk of E sits in hom from E star times dk to xk. And the additional conditions one needs to satisfy if one has an element in hk minus 1 and wants to extend it into an element of hk will lie in hom t times, E times star times dk minus 1 to xk. And we have k minus 1 of those conditions. And we have hom of E times star times dk into xk minus 1. And we have k minus 1 of those conditions. So basically we here have a simplicial, co-simplicial thing, because we have something simplicial here in the first slot, here something simplicial in the second slot, and we can kind of interchangeably apply D's and S's. So the maps here are S of x and D of D, and the maps here are S of D and D of x. So basically the whole proof of the representability is the fact that if this one is representable, then this one is representable. So we're doing it inductively.
What's your exponent on your second factor? Is like pushed against the edge of the board.
This thing here?
Yeah.
It's k without 0. So it's the numbers from 0 to k, and we omit the number 0. So the good thing is, almost everything in this diagram is representable. So we know that hom from d into something is just applying t1 on the right hand side, and we can do that k times. Same here, and this one will be representable by induction hypothesis. So I'll write the same diagram, but kind of in represented form. So we have yeah, so I hope it won't be a problem. No, you're right, this diagram is too important. Thank you. So I want to show that H is representable.
Yes.
So I will show that HKE is representable by induction.
That I understood. I mean, like, what the meaning of HKE is.
I don't have a good intuition for it. It's basically a little bit like one can, in a simplicial manifold, kind of, like build simplices out of lower dimensional by iterative horn filling. So my intuition that this is somehow, yes, but I cannot make this precise in any way. So we have HK minus 1, T1K T1K xk here, corresponding to that one, and here we get T1K minus 1 xk to some power, and T1K xk minus 1 to some other power. And we have a map here, and if it was a surjective submersion, I could end the talk and we could go to the coffee break. The problem is that this map is very non-surjective. And basically, in order to solve the co-representability, we're going to find that HK minus 1 maps into a very nicely looking object inside of here, which lies in the image of T1K xk.
Is this supposed to be a pullback diagram?
Yes. So yes, so this is a pullback diagram. The conditions that something in HKE has to satisfy are exactly those of HK minus 1 plus the last component. And I'm now going to write down the thing which should be intermediate. It should be T1 kxk, but we forget about the top component, so we tkxk. There will be a fiber product. And the other component is T1 kxk0. And the fiber product is T1 kx0, forgetting about its top component. Sorry, this is not injective, of course. This is just a map.
When you take the fiber product, is that say T1 to the kx?
Yes, it's T1 applied k times 2. So, and the fact that we are mapping into xk0 is somehow relatively immediate. Basically, if we have xk, it projects to the xk0, which naturally sits inside xk minus 1 to the power k without 0. And then we use the fact that T1 has an adjoint, so limits are preserved. The fiber product bit is also kind of a little bit of diagram chasing. The part which actually, to my understanding, is the complicated one is this bit. So, complicated bit. T1 xk tkx k is the limit of I'm trying to prove that if I have a diagram which I'm currently finishing, and I have something which fits into the diagram, it has a unique natural map into here.
I mean, you're trying to exhibit this as a pullback, but isn't this already a manifold? I mean, you're just removing something from it, which is like...
basically, the hard bit is saying that this one lifts uniquely here.
In order to do that, you use this pullback diagram.
Yeah.
I see.
So, and now you'll notice that I have started using another notation for the sigmas, and that's because they are not quite just degeneracy maps, because this thing here, it was hom of point times dk to xk, not dk plus 1 to xk. So there is an additional first degeneracy which behaves different from the others. Okay. Now I'm using the result, which is unfortunately erased, about splitting T1 of graded manifolds, because we're just now going to split T1k xk by using the same connection over and over again. And that will give us that the function of T1 k xk is the sections of the symmetric power of certain dual of a vector bundle, and the vector bundle will be a bunch of copies of Tm, and the copies are indexed by subsets of the set from 1 to k. And it's not 0 to k exactly because of this first degeneracy which is missing. By using this language, we can kind of now go from forget about graded manifolds and do all the calculations with graded vector bundles. And the phase and degeneracy maps just become shifts on multi-indices. So we have a multi-index big I, and when we apply the jth map, we're actually just pushing to the right all indices that come after j minus 1. And similarly, when we apply sigma j, we are basically just taking something in the component big I and pushing it into the component where we are pulling back all indices right from j by 1. Sometimes this will be 0, so this is 0 if j and j plus 1 are in I. Basically, if the slot is already occupied, the element vanishes. And also, S0 of Vi is 0 if 1 is an element in the multi-index, because we are in point times decay. So, and the statement we want to make is basically this pullback statement, which now reads as follows. Given V0 to Vk minus 1 in V k minus 1, such that sigma I of Vj plus 1 is sigma j of Vi for all the reasonable ij's. There exists W in Vk such that sigma I of W is Vi. And this is a purely combinatorial thing now. So, but the combinatorics are not completely trivial. And I should note that, so there have been attempts to prove the main theorem in the literature, and to my knowledge, this is exactly the statement where those proofs are incomplete. Basically, this is usually checked only of multi-indices of length 1, which is in some sense the easiest case to check. And for multi-indices of higher length, one needs a combinatoric argument. And the combinatoric argument works as follows. We note that the above equations can be rewritten as follows. Oh, I should. And put the lexicographical order on multi-indices and then show step by step that we can solve those equations for W. Work lexicographically. Backwards. Define Wj to be V0 J like this when 0 and 1 are not in J, and Wj as Vj I minus Wj I plus 1. Okay, I wanted to write down this formula because in it one can see the crucial bit. It's that we can define Wj by a formula that only uses the v's and multi-indices which are later than the multi-index j. And this is kind of what lets us actually proceed with the induction. And then there is a 2-page checking that everything stays consistent with each new definition. So, dot, 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 dot. And. So, using that, we can show that T1k xk, if we remove the top layer, is a limit of certain diagrams, that the hk minus 1 maps into this subspace. We can do the same for the other component. We can show that it's even in the fiber product. Then we are in a case of a surjective submersion where the fiber will be exactly the kernel of the Horn projection shifted into degree k. Homework question: how does one see in this proof that we have no condition on the very top layer on the full multi-index? And ooh, that's fancy. A tablet telling me how much time I have. Okay.
So,
yes?
can I ask you, what is M with respect to the simplicial manifold X? I'm lost.
Oh yeah, thank you very much. M is xk. Sorry,
Is it the whole? M is the whole or just X is 0?
It's here. It is actually xk. So this is probably 1. Yeah. So the whole part works only on a fixed manifold. We don't need at all the simplicial structure on X. We just need a fixed xk to formulate this. Okay.
So the mass HK minus 1 into that other fiber product, and the other thing are those are transfers or something?
The map into the fiber product is actually, I shouldn't have.
I mean, like, doesn't solve the problem.
Yeah, no, you're absolutely right. Actually, I denoted the errors the wrong way around. This is non-surjective at all, otherwise it would be trivial, and this one is surjective, because we're basically exactly, so on this component.
Surjective, you mean submersion?
Yes, and yeah, because xk0, from xk to xk0, we have a surjective submersion, which means we can pick compatible connections, which means that we can kind of, like in a very elementary way, check that it's actually a surjective submersion. And yeah, the kernel here will be, yeah, the fiber. Will be kernel of pk0 in degree k. Because this part forgets degree k, this part forgets the kernel of the Horn projection, and but we have both information, so the information missing is exactly in the intersection.
I have no idea what you mean by kernel.
Sorry, on this error we can work in the category of graded vector bundles, and then
Okay.
kernel is well defined.
Okay.
Okay, maybe I'll just stop with the remark that this is not the end of the story. Now, of course, we know that, so this is the first consequence. We knew that on H, we have a D action, which means a homological vector field. So now we know that we have a homological vector field on the graded manifold associated to the tangent complex. So now it would be nice to have an explicit description of the brackets of it, which I hope to be able to talk about at some future event. It's work in progress now. Thank you very much.